After knowing what is an algorithm is, the next step is the fundamentals of the analysis of algorithms efficiency. So when we study an algorithm, the next step is to make an analysis of an algorithm. So that is why the subject itself says it is a design as well as it is an analysis of the algorithm. So let us see the first topic here, the analysis framework. So what are the things we need to study in the analysis framework is measuring an input size, then units of measuring running time, then the orders of growth, and after that, so we need to find out the worst case, best case, and the average case efficiencies. So here, when we talk about the analysis framework, so we need to find out two kinds of efficiency. So that is, one is time efficiency, which indicates how fast an algorithm which is in question that runs. So this time efficiency is also called as time complexity. Then coming to an another efficiency thing, so that is space efficiency, which is also called as space complexity. It refers to the amount of memory units required by the algorithm in addition to the space needed for its input and output. That is, how much an extra space needed by an algorithm, whether the algorithm is holding more number of space in the memory, so that will define the space efficiency of an algorithm. So now, so when we start about finding an analysis of an algorithm, so the very first thing here is, so usually we have to measure the time efficiency, that is how fast the algorithm which we have designed or which is in the question which is going to run. So anybody who is going to choose an algorithm doesn't choose an algorithm which runs very slow, is it right? So that is why with this analysis part that is attached to an algorithm, so we can get to know whether an algorithm is running fast or not. So with the help of this, so we can choose an algorithm in a better way. So usually instead of space efficiency, we always measure time efficiency. So time efficiency is the most important thing here. So when we start finding an efficiency, that is time efficiency of an algorithm, the first step is measuring an input size. So let us see how to measure the input size. So when we start with the obvious observation that almost all algorithms run larger on larger inputs. So this is an obvious observation. So with the more number of inputs given, that is when the size of the input increases, as well as the running time of your algorithm also increases. This is an obvious thing. So for example, so if we have a larger array, so sorting will be taking more time, because as the number of array elements increases, the time taken to sort the element also increases. This is an obvious observation. And the second example is multiplying a larger matrices. So when you have given a small matrices, you can multiply that matrices very easily. So when the large matrices has been given, as the size of the matrices increases, so the time taken to make the multiplication also increases. So therefore, it is logical to investigate an algorithm's efficiency as a function of some parameter n, that is indicating the algorithm's input size. That is, very first thing is we have to see what is the size of the input which we are going to give. So in most cases, so selecting what is the input size, that is a parameter which is going to indicate it as input size, that is quite straightforward. For example, if we take the problem of sorting, for sorting What is the input we are going to give? So that is an array of elements, a list of elements we are going to give. So that is a simple thing. So there the size means, so the number of elements you are going to give, that indicates the input size. This is a quite obvious one. Then coming to the next problem is searching and finding the list of smallest element or the largest element. So these problems, sorting, searching, finding the smallest element, finding the largest element, in all this kind of problem, so we are going to give a number of elements. So the number of elements which you are going to give, that indicates the input size. That is an obvious one, that is n. Then coming to the, for example, the problem of evaluating a polynomial, so which I have written here. So this is a polynomial written. So in this polynomial you can see that, so this is of degree n. So it will be the polynomial's degree or the number of its coefficients. So number of coefficients are, that is a of n minus 1 up to a of 0. So you can note here that, so whether we can take n as the input size, or we can choose the number of coefficients which is one larger than n. So we can choose any one of these. Either we can choose n as a parameter of input size, or we can choose n plus 1 number of elements will be there, that is indicating the number of coefficients present in the polynomial. So then comes the next thing, so that is in some other situations, so where the choice of a parameter indicating an input size does not matter. For example, computing the product of two n by n matrices. So there are two natural measures of size for this problem. The first and more frequently used is matrix of order n. So here we can take n as the input size. And the other natural contender here is the total number of elements in the matrices being multiplied. So since there is a simple formula relating these two measures, so we can easily switch from one to another. That is, either you can take n, that is n cross n. So n will be the input size of the matrices, or you can take the number of elements which you are going to multiply, so in the matrices. So we can use any of the measure. So that is one thing. So then comes the choice of an appropriate size metric can be influenced by operations of the algorithm in question. So for example, how should we measure an input size for a spell checking algorithm? So if the algorithm examines individual characters of its input, we should measure the size of number of characters. Otherwise, if the algorithm is working on the words, so we should take, so the number of words present in the given text as the input. So in this way, there are many ways to measure an input size, and we have to wisely choose which one we are intended to measure. So some of the other algorithms for which, for example, checking the primality of a positive integer n. Here, the input is just one number. So that is whether the given positive integer is a prime number or not. But its number's magnitude that determines the input size. So in this way, there are many ways to find the input size, and we have to choose by using any one of these methods, and we have to come to a conclusion that in which way we are going to measure the input size. So after measuring the input size, the next thing we are going to find out is, so the units of measuring running time. So the units of measuring running time means, so we have a standard unit of time measurement, that is a second or a millisecond and so on. So that is an obvious one. So when we are measuring time means, so either we have to go with measuring in the seconds or in a millisecond to measure the running time of a program implementing the algorithm. But there is an obvious drawback to such an approach. So what is that means? So dependence on the speed of a particular computer, dependence on the quality of a program implementing the algorithm, and the compiler used in generating the machine code, and the difficulty of clocking and actual running time of the program. Since we are measuring the algorithm's efficiency, so we would like to have a metric that does not depends on these things. So when we can measure the algorithm's time exactly, that is when we feed this algorithm to the computer. So how we are going to feed this algorithm to the computer means, that is in the format of a program. So here there comes the many things come into the picture, that can be the program, the implementation of the program, or it can be a compiler that is going to generate the machine code, or there may be a difficulty in clocking, or the speed of a computer. So many things come to in picture. So this is where, when the algorithm has been converted to a program, but here we are just measuring the algorithm's running time, so that we need no need to depend on these things. So here, that is why we will find an approach to find the unit of measuring the running time, that is what we call it as a basic operation. So this is to count the number of times each of algorithm's operations is executed, but we will only measure the basic operation in an algorithm. So then what is a basic operation of an algorithm is? So this is the operation contributing the most to the total running time, and compute the number of times the basic operation is executed. So let us find what is the basic operation in our algorithm, and after that what we can do is, we can find how many number of times this basic operation is going to run. So that is going to give you the time efficiency of the algorithm. For that there is a formula, that is T of n is approximately equals to C op into C of n. Here T of n, so which indicates the running time of a program implementing this algorithm on that computer, and COP, that is the execution time of an algorithm's basic operation on a particular computer, and Cn is the number of times this operation needs to be executed for this algorithm. So this is the formula to find out the time efficiency of an algorithm by finding the number of times the basic operation has been executed. So basic operation is nothing but it is an operation which is contributing most to an algorithm. I will tell you an example. So when we are searching an element in a given list, so what is the basic thing we are going to do there? So searching an element means, so we just compare the key element with the list elements given. So here the basic operation is comparison, right? And also, so sorting an elements, how we sort the elements, that is we are going to compare the element with the other element, then only we will going to find the place of an elements in the given list in a sorted order. That is, if we are sorting an elements in an ascending order, we know that the smallest elements should be placed in the left to right. Is it correct? So from left to right, the smallest to the largest element, and we know the smallest element should come to first. So there comes the comparison. When we compare two elements, then only we will get to know which is the smallest and which is the largest. There comes the comparison, right? So when we take the multiplication of matrices, there comes the two operation. So we know how to multiply two matrices, so we need to make multiplication as well as addition, but this is multiplication of algorithms, so we can take multiplication as the basic operation. In this way we have to come to a conclusion that which will be the basic operation. So in an algorithm there may come many operations, but we have to decide which is the basic operation that is most important in an algorithm, and we need to find out how many number of times this basic operation will be executed. And this is how we are going to measure the time efficiency of an algorithm. After that, there comes the order of growth. So order of growth means this is in a ascending order of slow algorithms to the fast algorithms. So sorry, it is in the descending order. It is in the descending order. First comes the fastest algorithms, and then comes the largest, that is largest running time, that is nothing but the slow running algorithms. So here comes the comparison. You can see here. So if we take n, that is 10, 10 to the power 2, 10 to the power 3, 10 to the power 4, 10 to the power 5, 10 to the power 6. So suppose this is the input size if there is n. So you can see here, if an algorithm's running time is log n to the base 2, you can see if the input size is 10, it is just 3.3. And you can see if it is 10 to the power 6, it is only 20. So which indicates that even if the input size is 10 to the power 6, its running time will be only 20. So again you can say if the running time is n to the power 3, it is 10 to the power 18. You can see the difference here. So that is why an algorithm's efficiency, if it is log n to the base 2, that is an fastest algorithm. If it is going to be n cube, it will be very largest one. And you can see here, if it is 2 to the power n, just for 10 square, that is for 100 numbers which you are going to provide as an input, you can see here 13 into 10 to the power 29. And if it is n factorial, it is 9.3 into 10 to the power 157. So you can see if the input size is 10 to the power 6, so what will be these numbers? So that is why, so if your algorithm's efficiency is log n to the base 2, that is an fastest algorithm. If another algorithm, for example, if we have a problem of sorting, and if your one algorithm is going to give log n to the base 2, and another algorithm's running time is n factorial or it is n cube, don't choose the algorithm whose running time is n cube or n factorial or 2 to the power n. Choose an algorithm which is having a least running time, that it will be the fastest running algorithm. Everybody wants the fastest running algorithm, so that is why go and choose the algorithm whose running time is small. So that can be log n to the base 2, or it can be n or n log n. So if you go beyond this, so the running time will goes to be expanded as your input size is going to take the larger numbers. So if an algorithm is running with the n factorial, if you just give 100 number of elements as an input, you can see that its running time is 9.3 into 10 to the power of 157. So that will be, we can say that it is running very slowly, that is its running time is so much. So in this way you have to choose an algorithm. When you have choices of one or more algorithms, you can choose that which will be the better algorithm is. Then coming to the worst case, best case and average case efficiencies. So when we have an algorithm, so anyhow we are going to measure the input size, and after that we will find the basic operation in an algorithm, and we will see how many times this basic operation is going to be running. So based on this we will find the running time of an algorithm, but this is not the case always. by measuring the input size, by measuring the basic operation and how many number of times this basic operation is running. This is not only going to give you the time efficiency, there arises the situation of best case, worst case and average case efficiencies. Let us see it with an example. So what is this best case, average case and worst case efficiency is? Here is an algorithm. So let us first see how to write an algorithm, the usual notation we are going to follow in rest of the classes also. So first we will going to write algorithm, that is in the capital letters, the keyword, and after that we are going to write the algorithm's name, followed by in the brackets we are going to measure the inputs, and after that we are going to write the three comments. So first will give you the aim of an algorithm, the second comment is going to give you the input of the algorithm and output of the algorithm. So we know with the basic things we studied with the algorithm, we know that we have to precisely mention for what input our algorithm is working. Precisely we have to mention. So here we have to mention what is the input we are going to give, so for which our algorithm is working properly. So here is an example of sequential search. So sequential search means, so here we have going to be given an array. For example, here I will write some array elements. So here you can see I have written an array of elements, so which we can index from 0 to n minus 1. So I will write here 0, 1, 2, 3, 4, 5. So there are 6 elements, so which is indexed from 0 to 5, that is n minus 1. And we have to going to give a key element which we need to find in this given array. So that is using a method that is called sequential search. Sequential search means, so sequence one after the another. In a sequence we are going to search. For example, if I have going to give the number 12 as a key element, so how we are going to find that element in the given list is with the sequential search approach. That is, first I will compare 12 with 10. No, it is not matching. So I will move to the next element. I will compare 12 with 7. No, it is not matching. Next I will move with the next element, that is 8. 8 is compared with 12. It is not matching. Then we will move to 6 and it is not matching. Then we will move to 12. Now it is matching and we will tell that the given key element is present at the position 4. Suppose if I have given the element 15, so what we are going to do? We are going to compare with 10, 7, 8, 6, 12 as well as 17. And we have to come to an end of an array and we can tell that, so the array element, the key element given, that is 15, is not present. So here let us see the algorithm. So the aim of the algorithm is searches for a given value in a given array by sequential search. And the input is an array A of 0 to n minus 1, that is indexed as 0 to n minus 1, and a search key that is called k. So the output is the index of the first element in A, that is the array, that matches k, or minus 1 if there are no matching elements. So you can see here, so it is the first element in A. So suppose if I have written 12 again here, and if I going to find 12 means, so this is the index which is going to be given. Why? It is the first time we are matching. When we match it first time, that is the index has been given, even the elements has been repeated. Even the elements has been repeated, this algorithm works well, but is we are just going to print the output as where we are going to find the element for the first time. So here let us start with I is equals to 0, and while I is less than n and A of I is not equals to k, we just want to increase the value of I. I means the index value. Index value starts with here and we will check I is less than n. So n value here is 7. So there are 7 elements. 0 is less than 7 and we are going to compare A of 0 with the given key element, for example 12. No, it is no matching means I will be incremented. I comes here. So seventh element will be compared with 12. 7 will be compared with 12. No, it is not matching. Then I will be increases. I increases here. Again we are checking whether I is less than n. Yes, 2 is less than 7. And another condition is a of I is not equals to k. So what is a of I? 8. 8 is not equals to k, that is 12. So then comes the increment of this index value. Where this while condition stops here is, so you can see whether I is less than n should happen. That is, when it happens means we will going to beyond the array. So suppose if I had the given key element is 15, you can see here. So we will compare with 10, 7, 8, 6, 12, 17, 12. No, it is not been matched. Then we are incrementing the I value and we will check here. That is, with the 7th element, I will be incremented to 7. 7 is not less than 7. 7 is equal to 7. There fails the condition. So another thing where this while condition fails is when a of I is equals to k, that is matching the elements. Either you have to match the element, otherwise you have to go beyond your array. Then this while loop falls and we come out of this, and we will check if I is less than n. So we will return I, otherwise we will return -1. If we are returning I means we have found the element at the position I. That can be 1, 2, 3, 4, 0, anything. It is -1 means, so it tells that, so the given array element is not at all present. So this is an algorithm that is for the problem of sequential search. So let us see. So what will be the input size for this algorithm? So we know that, so there is an array with n elements, so that will be the input size n. So can we see what will be the basic operation? So basic operation here is the comparison. So searching means comparison. 12 will be needs to be compared with 10, 7, 8, 6 and 12. And there we find. So comparison is the basic operation here. So comparison. Let us see then how many number of times this comparison operations happens. So here comes the best case and the worst case and the average case efficiency. Suppose if the given key element is equals to 10, how many number of comparison is going to happen? So there is only one comparison. Suppose if the key element is equals to 6, how many number of comparisons? 1, 2, 3, 4. Suppose if the key element is equals to 17. So how many number of comparisons we are going to make? 6 comparisons. Suppose key is equals to 15, which is not at all present here. 1, 2, 3, 4, 5, 6 comparisons. So see. So if the given key element is at its first position, the comparison, the number of times the basic operation has been executed, that is 1. Suppose if the given key element is at the last element, then also we have 6 is the number of comparisons. If the given key element is not at all present, that is when there is an unsuccessful search, there is also 6 comparison. So that is nothing but n comparison if there are n number of elements. This is equals to n and this is 1. So this is an best input, and we can say this is the worst case where your algorithms running, that is the basic operation, is running more number of times, and here your basic operation is running least number of times. So this is the best case input and the worst case. So here the number of times the basic operation does not depends on for only one type of input. So it depends on different types of inputs. For different type of inputs, the efficiency is different. That is why we are going to tell that as an worst case and the best case efficiency. So let us see the definitions here. So the worst case efficiency of an algorithm is its efficiency for the worst case input of size n, which is an input or inputs of size n for which the algorithm runs the largest among all the possible inputs of that size. So if the key has been either it is in the last position or in the given key element is not at all present, so that is what the worst case. So you can see here C means comparison worst of n. N is the number of inputs, that is equals to n. So if there is 6 elements means, so that is the 6 is the number of times we are going to make the comparison. So then comes the best case efficiency of an algorithm is its efficiency for the best case input of size n, which is an input or inputs of size n for which the algorithms runs the fastest among all possible inputs of that size, that is C best of n is equals to 1 if the given element is present at the first position. So based on the algorithm and the input we are going to given, so the efficiency of the algorithms also differs. So this is how we are going to measure the analysis of an algorithm. So here we need to mention both the worst case and the best case. So average case means that comes in between the best case and the worst case, and usually we will not going to measure the average case efficiency of most of the algorithms. So whenever we are having these kind of cases where we need to find out whether the best case is really there or the worst case is really there, so we are just going to measure the best case efficiency and as well as the worst case efficiencies of an algorithm. For some of the algorithms this may not be the situation, so there comes only one running time for the algorithm. So whatever the input you are going to give, the running time will be same. So those kind of algorithms may also arise, but for some algorithms we need to find out the worst case and the best case. This is how we are going to find out the efficiency or the analysis part of an algorithm. So here there is an algorithm given means, so we have to find its efficiency to know that how fast the algorithm is working. So after this, so we will see some concepts that is related to analysis also. After that we will see some of the examples of finding the efficiency of the algorithms. So after that only we can move to the algorithms and we can see how best the algorithm is in its analysis part. Thank you.